Should I start?
Yeah, sure.
Okay. Okay. Yeah. Thanks a lot, everyone. Thanks, Adit, and especially for giving me this opportunity. And yeah, I'm Sridutt Bhalachandra, and I'm a senior architect at NVIDIA. And before this, I spent about 4 years at the National Energy Research Supercomputer Center at Berkeley Lab. And my area of research and specialization is energy efficient high performance computing or green supercomputing. And today I'm just going to talk to you all about the work that has been done and yeah, the same topic, right? So to begin, the title of my talk, as you can see, is green supercomputing. And why is it important? It's important because uh, at this point in time, more so than ever, efficient and sustainable computing um, is very pertinent and important because that will be necessary for creating a greener future for everybody. So, um, yeah. So let me just begin by giving you a small refresher or a one slide intro to what supercomputing is. So right now, many of you might be using laptops, and the typical laptops have like 4 to 16 processor cores, and supercomputers have millions of cores, right? So this here is the Perlmutter supercomputer at NERSC, and this is one of the supercomputers that I worked on. And what it has is that it has close to 500,000 cores, and then the question is, why do we use them, right? So the first thing what you can think about is each one of you might wake up every day in the morning, check your phone and look at the weather or the temperature for that day, and the forecasting and the weather simulations are on these large supercomputers or data centers that provide you that information that you infer on your phones. The second thing is you might have seen the latest supercars or jets coming through, and to build them, you need to do a lot of simulations in the designing phase, and that is run on these large supercomputers. You might have heard about genome sequencing, drug discovery. New drugs are being formulated every day, and that process is very compute intensive, and they make use of large supercomputers or large computing systems. And finally, to address the elephant in the room, everybody knows about ChatGPT and the recent advances in chatbots, for that matter. When you open your prompt, you write a thing and you get the answer. Um, Before that happens, which is called as inferencing, a large training of these machine learning models or the deep learning models need to happen, and they are running, and that happens on massive amounts of compute, and those are facilitated by these large supercomputers or data centers that you might have heard of, right? So what distinguishes from your everyday computing that you do on a laptop to that of a supercomputer is the size and the speed. So now that we have heard about the good things that supercomputing brings us, um, supercomputing also are very power intensive or very hungry, power hungry systems, basically. And due to these, there is an energy crisis. So the supercomputers or the machine learning data centers that you might have heard of consume vast amount of power, often comparable to small towns. So I don't know if any of you have heard it, but if you have heard, about the Frontier supercomputer at Oak Ridge National Labs in Tennessee. That is the first exascale system in the world, and it's like the top system right now, and it can do like 10 to the power of 18 operations per second, and it consumes like 21 megawatts of power in doing that, right? And which is equivalent to the electricity usage of around 20,000 homes or medium-sized city, right? So now that we are in the exascale era, the next frontier is something called as the zetascale, right? Which is like 1,000 times more faster than what we are at right now. That is the exascale, which will be like 10 to the power of 21, right? And what I'm showing you here is a graph of the energy efficiency that we have achieved over the past decade. And there is a notion that we might have our zetascale supercomputer maybe in a decade, right? And if we were targeting like 2034, that is for 10 years from now, if we were to just take the current exascale computer and align and build multiple copies of that so that we have exascale system, given that the current exascale supercomputer consumes like 21 megawatt, you would be looking at a power consumption of about some 500 megawatt, right? And a nuclear power plant has like a 1 gigawatt capacity. So you would essentially need uh, uh, a half of the nuclear power plant just to power that system, right? So this ever more increasing power budget for the supercomputers is not feasible anymore, and whatever needs to be done needs to be done by only increasing the power consumption by a considerable amount, right? And you cannot just go on building supercomputers that are not sustainable. So that's why energy efficiency is ever more important, right? As we want to build larger and larger systems so that we can tackle even larger and more complex problems in this world, and like even push the boundaries of science and humanity, correct? So because of these massive energy consumption that we see, it has an impact on climate change as well, right? Many data centers still rely on fossil fuels, contributing significantly to carbon emissions, right? And the data centers right now, if you look at the DOE report, they consume about 2% of the total US electricity. And if you look at the EPRR report for 2030, this is supposed to grow fivefold and reaching up to 10% of electricity that is produced in the US, right? So it makes more sense that the computing that we do starting now and moving into the future is more sustainable and greener, right? So that's why like the green computing is more and more important moving forward. Okay. Yeah, if you have any questions, feel free to ask them, pause me, or as Adit mentioned, ask them on the chat and I'll be happy to answer, or we can come to those questions at the end of the talk. Okay. So what is green supercomputing, right? So green supercomputing is pretty simple. It involves designing and operating supercomputers and data centers with a focus on energy efficiency and sustainability to minimize environmental impact, right? I do not know, but if you can raise your hand or something like that, if you have heard about this, there are initiatives like something called as Green 500 and ML Commons right now that are trying to help quantify and improve energy efficiency and sustainability in supercomputing and data centers, among others. And they are helping or trying to help us to achieve more efficiency so that the computing that we do is more greener and more sustainable as we increase the amount of computing that we do in the future. And what are the examples of green supercomputing for that matter, or green data centers, right? So if you go to the website right now and you Google it, right, top500.org, that's like the top 500 list, which tracks the top supercomputers in the world right now, right? And as part of that list, there's another list called as the Green 500 list. It also tracks the most green supercomputers in the world. And the current supercomputer that is the most energy efficient is called JEDI, and it's at the Hewlett Supercomputer Center in Germany. And it is a prototype system, much a smaller system to a large supercomputer, exascale supercomputer coming up in Europe right now called the Jupiter, right? The second example is in our Bay Area. I assume everybody is local, so I'm just quoting examples, and it's near and dear to me because I worked on this. So the supercomputer at NERSC, which is the Perlmutter supercomputer. You might have heard of Saul Perlmutter from the Big Bang Theory as well. So it is named after Saul Perlmutter, who gave the evidence or proved the Big Bang and got the Nobel Prize for it. And the supercomputer is named after him. That supercomputer utilizes evaporative cooling. So most of these supercomputers, because they consume so much of power, right, they get pretty hot, right? And if you have heard about, like, if you have built a desktop by yourself, you generally use fans or coolants and stuff like that, right, to keep these systems cool, right? Similarly, because the supercomputers consumes massive amounts of power, generally people use chillers for that matter, and they are not always efficient, and that's why the carbon footprint and increases. But the Perlmutter supercomputer, it takes advantage of the temperate climate of the Bay Area, and it's on the hill. If you ever go there, you might have seen the Lawrence Hall of Science. If you go in the East Bay, and it's just below that, and so the cool air blows in the bay, from the bay, and it takes advantage of that, and because of that, it does not use chillers, and it takes into makes use of the natural coolness of the environment to maintain optimal temperatures, and that in turn makes the NERSC facility that is being run in the Bay Area the most energy efficient facility in the entire DOE, Department of Energy complex, right? So I don't know if you have heard about the term called PUE. It's a very famous term to measure the effectiveness or the energy efficiency of these supercomputers. It has a PUE of less than 1.1, which is for every 1 unit of compute you do, you only waste about 10% of power or energy, right? So it's like 1 unit, 1.1, right? And most of these exemplary data centers are in that particular range, right? So, and it is like at times 1.08 or 1.07 at times is what we have observed when I was working there. And the overhead that you see is only about 7%, right? But in contrast, some of the computers which are not using these sustainable practices, their PUE would be like 1.4, 1.5, 1.6. So for every amount of compute that you're doing, you are spending like one amount for the actual compute and about 60% overhead on other things here. So we're essentially wasting that power, right? And also, if you might have heard of Project Natick, if you're not, then probably Google it, and there's a cool YouTube video. So what they're trying to do is on the shores of like Scotland, what they're trying to do is like they are trying to build data centers by submerging it into water. So it's like in a capsule kind of a thing, and they just submerge it into the water, and the idea is, and because the water temperature is pretty low, or it does not change like during summers or during the winters, they are trying to make use of the natural cooling of the ocean water to enhance energy efficiency and while minimizing environmental impact. Okay. So these are a few examples, and there are multiple more examples if you can look at, and people are very serious about this and trying a lot to improve the energy efficiency, because there's no other way apart from that, right? So what are the elements of green supercomputing, or how do you go about building better data centers, right? So there are a bunch. This list that I'm going to show is in no way exhaustive, but I'm going to show you some of the examples how you can go about building like better data centers or supercomputers, right? One is obviously hardware optimization, right? So if you upgrade to newer energy efficient hardware, you can reduce the energy consumption. That's true with most of our appliances, right? Even if you have a AC or a water unit or heating unit, they say, oh, upgrade it to a more energy efficient one. So every generation of hardware you put in, you basically uh, the manufacturers know and they optimize for that, and that in turn helps you to improve the energy efficiency for data center, right? The second thing, the most important thing, if you're not into hardware, and I think a bunch of you might go out there and become software engineers or software developers, right? Right. So is developing software with energy efficiency in mind and not just performance, right? So there are ways to improve software, right? And in a way, when you improve that software's energy efficiency, you can actually improve the performance as well, right? So this includes like using algorithms that minimize resource computation. And when you are running these massive supercomputers, right? I don't know if any of you have run on a supercomputer, but you just can't start an application and start running it, right? There are many users who are using the supercomputers, right? So you basically submit a job, or you say, I want to run this particular job, and it has to be scheduled by a scheduler on the different computing resources as they become available, right? And the scheduling is a very hard problem, and most of the time, uh, what you say in the past, or to begin with, it was always designed, schedulers were designed to improve the performance or the utilization, right? But if you have energy aware schedulers which think about energy efficiency and stuff like that, you can improve the energy efficiency of the supercomputers and optimize the server workloads, right? But basically, think about it, right? You don't want any portion of your supercomputers to be idle, correct? So you can basically bring together a bunch of jobs, run on a smaller set of supercomputers, right? If you can co-locate them and coalesce them together, and you could basically turn off servers which are not being utilized, right? So that can improve energy efficiency. Next is you can improve utilization, as I explained, like energy efficient workload scheduling, then reducing power variation. Like when you see a supercomputer is being run, and I told about like 21 megawatt is what the exascale system consumes, right? Imagine a job is running, and when you're running something on a system, right, the amount of computation that you do, right, will not always be constant, right? You might do some operations, then do some more operations, and the amount of intensity of the workloads that you do might be different, right? So that brings in a lot of power variation, and that spikes are bad when you're trying to optimize things. So you can reduce power variation, or as I had explained, you can consolidate by utilizing virtual technologies. You might have heard of VMware or virtualization, and bring together a lot of jobs together. So these are a few approaches. Finally, the other thing, what you can do is like monitoring and automation, right? If you can't measure stuff, you cannot improve it, right? So when you are running a, a data center or a supercomputer, it is very important that you measure how well it is doing, right? So if you instrument your data center as much as you can, and you get the data and you analyze them, then you can improve the running of the system or the data center that you have, right? An example for that is you can have temperature sensors, right? In the data center, rather than running it always cold to a certain degree, even if it does not require, you can see what is the current workload on the data center, and what you say, you can adjust the cooling based on the real-time temperature data that you have, right? So that can improve energy efficiency. And it will also avoid you from making things more overcooling stuff and wasting energy. Right? And as I explained to you, this cooling takes a lot of power. So I gave you an example of NERSC, which does not make use of chillers, right? So you can cool a system either by using just air, you blow air using a fan, or you can pass a liquid and take the heat from those systems and cool, or what you call is like a coolant, right? Basically, that you can use, right? So it has been shown that liquid cooling is more energy efficient and probably a better solution. So moving to such technologies like liquid cooling can improve the energy efficiency of the systems. And finally, I had explained like one of the reasons, like when I was introducing the energy crisis, is that many of these supercomputers are still running on like fossil fuels that increases the carbon footprint, correct? So you can use like more renewable resources like solar or wind power significantly reduces. If you have not heard about it, Apple has a large solar farm right now in Reno, Nevada, and it is utilizing it for its data centers and such things. So there are companies which are trying to do that, and transitioning to more renewable energy sources helps improve the carbon footprint of data centers, right? So again, this is not an exhaustive list, but these are some of the things that you can think about and doing it. And because you're students and many of you are also going to think about, oh, what I can do in the future. So these are some of the things, if you want to get involved into green supercomputing, something like that, these are some of the areas that you can do research in or come up with cool solutions which can really help take the frontiers of green supercomputing forward. So I wanted to showcase two of the work that I have been involved in, just to give you a glimpse of, and I know it looks very complicated, but I'm just going to simply explain. This is a work that I have done at Berkeley lab. So I'll give you an example of the work that has been done at Berkeley lab. And the second showcase I'll do is the work that we're doing at NVIDIA, just to give you a flavor of actual workloads, things that can happen. And if you have questions, I can answer it because I have worked on it or I'm somewhat involved in it, right? So, so the biggest problem that one of the data centers right now have is they are not able to utilize the amount of power they bring in, right? So imagine right now, like you have an appliance at home, right? And there will be something called as the rated power, correct? So it'll say, oh, the rated power is 100 watt or 80 watt, something like that, correct? So, and that rated power is the maximum it can use for something like that. But that does not mean that when you're running that system, it's always using 100 watt of power, right? The power changes based on how you're utilizing, and that's true for your phone as well, right? If you're using some a game or something like that is graphics intensive, you might burn, or watching a video, 4K video for that matter, you might consume more. But if it is in standalone, it will not use that, correct? So such are the loads that run on the supercomputers as well, right? So when they build a supercomputer, what you do is that there, as I said, there are millions of cores. So there are like, just like your CPU or a desktop box, there are thousands of such nodes that have these CPUs and GPUs in the supercomputers, right? So what they do when they build the data center is that they add up the rated power of these, right? And that's how you provision a data center. That's called as worst case provisioning. And that's also the most performant because you are giving it as much of power it would always require, right? But it's not like you do not play the game or watch a video always on your phone, right? The same is true with the supercomputers, right? You do not always utilize the system in such a way that you're going to always consume the highest amount of power, right? So what this is showing you is like the system power timeline for two of the supercomputers. This is the Perlmutter supercomputer on the bottom right, and this is the Cori supercomputer, which is the system before Perlmutter, right? So the rated power for that system for this Cori supercomputer here is in the dotted line, which is close to 6 megawatt, right? And you can see on average over the entire year, you are consuming only between like 3 and 4 megawatts. So it's like 60% of the utilization, right? So you're wasting this 40% of power and you could have used it to bring in more compute, right? Because if you're not using it, you're wasting it. You have already built the infrastructure to provide it 6 megawatts of power, right? And if you look at like this Perlmutter supercomputer, right, it is at about 3 megawatt, while the rated power is like 7 megawatt. So you're just using 40%. So you can see going from previous generation to the problem has even gotten worse, right? Going from 60% to 40% utilization. So while I was there, we were trying to think about, hey, we are going to, so at NERSC or Perlmutter or any other Department of Energy facility or data centers, they upgrade supercomputers every 4 to 5 years. So they bring in a new supercomputer. So the moment a new supercomputer lands right now, it's installed, people like us who work in different things, we'll think about the next supercomputer. So we try to learn from whatever is installed and see, hey, moving into the future, how we can utilize it, correct? So to give you a simple example, I'm much better off running this system at 4 megawatts, correct? Rather than 6 megawatts, right? But you can see if I do it at 4 megawatts, there are spikes which sometimes go more than 4. What happens if I'm not able to provide that, right? So it has to, so that's why therein comes the smart schedulers or the energy aware schedulers that I was talking about to provision. So that's the type of research that I was doing at Berkeley Lab and to improve the energy efficiency. Okay. I have some questions right now. Yeah,
You can
I'll
answer them either right now or at the end, whatever,
maybe I'll
whenever
take
you.
it. I have one or two more slides and I'll take them at the end. Okay.
Sure.
Okay. Yeah. And the next is like the NVIDIA showcase. So I've not spent. It's only been about 8 or 9 months I'm at NVIDIA, but I have had chance to participate in some of these things, not all of them, but in NVIDIA the focus on energy efficiency is very high. Because as you might have heard, like most of the supercomputers and large data centers are being powered by NVIDIA GPUs, right? So it makes more sense to make the hardware more energy efficient, right? So, but it has been shown time and again, when you compare to a CPU and a GPU, and if the code or the application that you're running on are suitable for the GPU, right? The power consumption of a GPU, if you look at like a CPU might consume like say 200 watt of power if you just look at it, but a GPU might consume like 400 or 700 so 700 watt of power if you buy it. But you might say, hey, the GPU is consuming more power, right? But the amount of computation that you can do per watt, that's how the energy efficiency is measured, is much higher on the GPUs than the CPUs, right? The reason is because GPUs are meant for purpose, a specific purpose most of the time, or the idea they were used for graphics, for example, right? That's why. And CPUs are more general purpose because they have to cater to all of the applications, while GPU has to cater to specialized applications. You can optimize GPUs more, and that's why they are more energy efficient, right? So that's what NVIDIA found out. So NVIDIA estimates that the data center could save an whopping 19 terawatt hours of electricity a year if all the AI and HPC and networking workloads were offloaded from CPUs to GPU and DPU accelerators. So DPUs are special accelerator types that are coming right now. I encourage you to go and read, at least Google DPU. It's very cool technology. So that's equivalent of energy consumption of 2.9 million passenger cars driven for a year, right? So that's the amount of impact that you can get because the per watt efficiency of the GPUs are much better. Then I told you about the Green 500 list. So the top 3 supercomputers, if I'm right now, if you look at the Green 500 list, are NVIDIA powered supercomputers, and the top 7 out of the 10 are again NVIDIA powered systems, right? And also, as I had told you, like the ML Commons is another effort that is trying to improve energy efficiency among these data centers. So right now, everything is about ML per for inference, right? Inference is basically what you, as I said, you ask a query, it gives you the answers back. That is called as basically inference, right? So I don't know if you have heard about NVIDIA Jetson called AGX. It's like Raspberry Pi, if you might have heard about, or system on chip, or the embedded computing type of the things. So within 1 year, from 2022 to 2023, the energy efficiency of these devices have improved 61%, and also the performance has improved 81%. So even there are strides that are happening in these low power devices. And these Jetsons you might have is being more and more used in like autonomous vehicles or like robots, like for doing robot motion planning algorithms and stuff like that. So they are being more and more used. So that's why it's more important. And to give you a contrast, these the entry level Jetson right now, or which is called as Orin or something, it consumes only 7 to 10 watts of power compared to a larger GPU, full-fledged GPU, which consumes like 400 or 700 watt of power, right? That's why you can use it on the edge in these robots or something like that, right? Because they need to be very energy efficient. And yeah, so how does the future look like, right? So the future trends are AI and ML are going to stay, right? Increasing use of AI, AI, AI and ML applications are going to be run on these supercomputers, and we might very well be end up using AI and ML to optimize the data centers operations to improve energy efficiency. So that looks like a future trend. And more data centers are expected to transition to energy, better energy sources like renewable energy, like solar, wind, of that sort. That looks like the thing. But what are the challenges? One is the scalability, right? Ensuring like when you scale things, etc., it does not always mean that you can have the same efficiency, right? That you can get from a low power device, right? Like again, that's an example for because when you make things big, you cannot optimize as much as you can when the things are small. So scalability is always going to be a challenge, right? So the demand for computational power is going to grow more and more, right? But that's why the other challenge will be the cost, right? You want always performance, right? But you will have to use these green technologies to basically deliver those high performance or the greater computer needs in the future, right? So how do you strike a balance between, say, the cost of implementing these green technologies, or basically the need for like higher performance? Some of these green solutions are right now expensive, right? So when you are procuring right now the system, you might say, I do not care. Let me buy like the not so efficient solution. But in the longer run, these not so efficient solutions end up like costing you more. But the human mentality is okay, let me do it later on, right? So So, but these are improving and the cost and the entry to barrier are becoming decreased. For example, I gave you an example of the liquid cooling versus air cooling. Liquid cooling is more expensive, but you still would want to use it because there are more advantages if over the long run, right? So yeah, so basically that's all what I had, and these are some of the references for the data and the statistics that I presented and some of the like the plots that I showed. Anyway, this thing is recorded, so maybe if you're interested, you can go there and take a look. And yeah, that's all I had. Thank you so much. I hope I was in the time and I did not go overboard, but it was nice. I'm very passionate about this topic. So yeah. So in case I missed the time. So yeah. And now I'll be
Thank you
happy.
so much, Sridutt.
Yeah.
Yeah, feel free to just answer the questions.
Yeah. So I'm going to answer the questions that I see in the chat right now, and you can tell me if there are questions later on Discord. Okay. So Chandra Ganesh says, I know it's probably very complex, but how do hardware improvements improve energy consumption in a low level way? Okay. So what happens is I can give you one example, right? So you might have have you heard? If you have not, then let's Google it. For example, you might have heard like right now, like when we initially had our supercomputer, even for the desktop or when the computing era began, right? A personal computer was so massive, right? And right now the mobile computer right now what you have is more powerful than maybe the big supercomputers that were there like few decades ago, correct? So how that we were able to achieve that is because of miniaturization, right? You might have heard about 3 nanometer, 5 nanometer, like the process technologies, right? You might have heard about, right? When it started, was like 20 nanometer was like where the transistors were made, right? Now they are to the size of like say 3 nanometer is right now. So they have shrunk in size, right? So when you shrink the transistors or through improved technology, right, you can fit a lot more transistors within that area, correct? And that basically makes things more energy efficient because you're still consuming that much of the same amount of area, right? So that's one of the ways you can example for how hardware improvements at a very low level can influence energy efficiency, right? And I can let me know, Chandra, if I answered your question, or else I can give more examples, right? Liam Tran asked, what do the upgrades for supercomputers consist of? So generally for supercomputers, it's like all bottom up, everything. So when I showed you like Cori and Perlmutter is what I was explaining to you at NERSC, right? There's no Cori anymore. So they basically, it's a transition, right? A new supercomputer is a new supercomputer. There are places, for example, if you might have heard about cloud service providers, right? That generally they are not. So right now, supercomputers they want to always get this what do you say, the best performance possible, right? But when you come to cloud service providers, you're okay with performance because it's general users also using it, right? And now you're not always running like high compute intensive operation. So for them, they might buy this. If you have seen a supercomputer, these are these large rows of cabinets or something like that, right? They might have a supercomputer cabinet right now. They might swap it for some upgraded part or something like that. But when it comes to these uh, leadership class supercomputers that are on the top 500 list, everything gets upgraded. You upgrade those cabinets, you upgrade the cooling, you upgrade the network. It's like complete upgrade. Okay. Uh, Andy Shea, I hope I pronounced the last name correctly. Does power consumption of GPUs and CPUs increase exponentially as the number of GPUs to CPUs increase? I wouldn't say exponentially, it's a linear increase, is at best, right? Because you're bringing more and more to them together, right? And right now, those are individual parts, right? So you're basically summing them. And So it's more linear is what I would say. But when you upgrade it, right? Like for example, I showed you the Perlmutter and the Cori supercomputer, right? Both were consuming about 3 to 4 megawatts of power, right? But Cori and the Perlmutter is almost 100 times faster in that same footprint, for that matter, correct? So Chandra Ganesh has another question. Can you explain what DPUs are in depth? I don't really understand what Google's definition are. Based off this Google definition, it is essentially a commander of an army of. So I don't know what. So DPU. I don't know what. So DPU is like a NVIDIA, you can search NVIDIA Bluefield for that example, right? So what it is, it's more like network, right? It's more used in a networking scenario, the DPU, correct? So I'll explain what it is, right? So when you have these large supercomputers that are millions of cores, right? And you're utilizing these and you're not using only one of these cores, right? To get the combined performance of these all of these cores, you have to run an application that spans the entire supercomputer, right? So there is a lot of communication that happens from one of these processors to the other, correct? So imagine there are millions of people and they need to talk to each other, correct? So there is a lot of traffic that happens. So there is a lot of data movement that happens. So these DPUs and of these other things, they help in connecting these stuff and routing the messages from the correct sender to receiver, right? And before, when the systems were small, right, you could basically take a wire from this to the other, right? And you could have connected it. Now imagine if there are millions of cores, you cannot connect each of the core with a million lines to the other, right? That's not tractable, right? So that's why you have something called as these DPUs or something. You might have heard about. It's a bad example, but I'm just giving it for easy routers or something like that, right? Like for example, they are routing the message and stuff like that. So basically, because of these computers are like becoming super massive and massive, the amount of computing required to pass on those messages has become more and more, and that's why these are also becoming very capable devices, right? So they can do some processing of the data and then give it directly to the sender, and rather than the sender receiving it and doing it. So that's how the DPUs are, and I think I tried to explain it in depth what Chandra wanted, but I'll be more than happy to explain that even further if you have. Ritvik has a question. Do you think we will have a supercomputer reach 1 PUE one day? It's again theoretical limit, right? Like probably, I don't know. Like I don't think so. Maybe I'm being a little pessimistic, but it's very difficult not to have at least a little bit of overhead, right? So even within 10% is very good right now. And there is so the PUE was proposed by something called a Google engineer or somebody called Chris Belady. If you can search him, Chris Belady, if you search his name. And that was done like decades ago, like that. It's called power usage effectiveness, how effectively PUE means. So he himself says right now the PUE has run its course and probably we need a better metric because you have almost reached like what is practically possible of that limit. Okay. Anand Datta has a question. What is the difference between the CPUs that consumers buy for mining and the GPUs that individuals? Yeah, so it's basically these supercomputers don't have to display something on a monitor or something, right? You might have seen like most of these. If you do a supercomputer, generally you will be using a Linux sort of a thing, a command line or something. Not that you cannot do submit jobs to it using GUI, but probably most of the time it is like a Linux. So you don't need the graphics capabilities of that, right? So the whatever the shaders and stuff like that, what you would require for rendering the pixels, those are mostly not there. And that, so when you build, if you're a system architect or a hardware architect, that portion of real estate that you have to design a chip is very, very, what do you say, small, or and you have to optimize it. So it is very expensive, right? So you would rather take those the graphics rendering kind of pipelines and rather give it more computing elements what we can use, right? So most of these have the same amount of power consumed, but in these supercomputers you do not you don't have the capabilities for rendering and stuff like that, and you use that part of the chip and add more computing units. That way you can improve, get more efficiency out of that. So that's mostly basically the thing. Also, it's like the programmability for example, for doing graphics, uh, because you asked it, you might have heard about ray tracing and stuff like that are very important. How ray tracing used for like simulating light and stuff like that, correct? And the software is mostly for these on the graphics are optimized for rendering and stuff like that, correct? But on the these supercomputers, they are more general purpose, that you can write a molecular dynamics simulation versus you can do like a weather forecasting and stuff like that. So it gives you more general interfaces for doing programming. So that's also a difference between these two. Chandraganish is, so you just keep the same computing power in smaller things. Yeah, essentially you could say that. Yep. Then the questions from Discord. I don't know who asked that, but I'll answer those questions. So the first question is, so in terms of energy efficient consumption so in terms of energy consumption, is the only way that we know of right now to generate enough power for next generation supercomputers, what you talked about in terms of energy consumption is the only way that we know of right now to generate enough power. Oh, so that's what. So no. I don't know. Again, I did not understand fully the question, but I'm not. I was giving you a nuclear power plant has that much of an output, but I was not saying is that these need to be nuclear powered, right? So they could be like powered by renewable sources as well, right? Like I gave an example of Apple, which has a 200 megawatt solar farm and Reno and stuff like that. And if you have a bunch of these solar farms, you can basically power that. But again, we do not want a 500 watt megawatt supercomputer. We would still want to be within 100 megawatt. That's why we have to improve energy efficiency, right? So because 500 megawatt is not sustainable, correct? So yeah. You talk about evaporative cooling when you talked about Microsoft. So I did not talk about evaporative cooling in terms of, when I said of Microsoft supercomputer, I talked it in terms of like the Perlmutter supercomputer at NERSC. So evaporative cooling is like where you're not using basically chillers. Okay, so it's very interesting if you get a chance to go to Berkeley Lab, and I think they have visitors, and I think you can go visit Berkeley Lab, and at times they show you the supercomputer as well. There's a NERSC visit also, so I encourage you to go there and try to see if you can go there. So what they do is that because it does not have chillers, there are massive cooling towers beside the supercomputer, and the water is taken up to a height and it's just dropped in this chiller. So it takes out, when you throw the water from height, basically it takes out the the heat from that water, and it's essentially evaporating the heat, right? So that's why it's called evaporative cooling. So again, I'm not an expert on that, but essentially, basically, because you're using these cooling towers and you're like just throwing the water from a very high to this low, you are removing the heat from that water and it's basically evaporating through because from this process, and that's why it's called as evaporative cooling. And you're not using essentially a chiller to cool that water, right? Because that's why it's not using chiller. That motion of just throwing the water from height to this one takes out the heat. So, but it's very cool technology. I would like to learn more when I get time, but you should explore that more if that does not answer that. My question that doesn't answer your question. So, do supercomputers have to be in good environments to be energy efficiency? Very good question. Specifically asking this about the Bay Area. Yes, agreed. Yes, yes. So, being in favorable environments helps. So, if you just write Google this same question, you might get people like post that build a supercomputer in Iceland. And actually they do, like, say, for example, you don't require cooling because we have ice, as they would say, or something like that. Yes. So having a favorable climate really helps. So right now, like, they're also trying to build supercomputers in Middle East, and as you know, in Middle East and countries, the temperature is very high, right? So that's why they're using solar power where there's a lot of sun for offsetting the carbon emissions and stuff like that. So yeah, very good question. Yes, agreed. So maybe because we are in this favorable climate, we are able to run such a nice data center, right? If it's in an unfavorable climate, you will not be able to have such low PUEs. So yeah, very astute observation. Yes, agreed. Yeah, I think that's all the question that I had. I think, yeah, so that is pretty much it. And I think I was hoping for like 15 minutes and like 5 minutes for questions, but there are so many questions that I really enjoyed answering them. But in case I went overboard, I'm sorry. I did not, if I did not respect the
No,
time.
no, don't even worry
Yeah,
about it. It was a really great and very informational.
yeah.
Yeah.
So yeah,
Okay.
that's, yeah. Are there any other questions which I can answer? And you can just speak up if you want, because we are at the end, if typing is a problem. Yeah. So what I can do is that in the chat, I think chat is accessible to everybody, right? So again, Adit, you can do that as well. So I'll write my email address here. So if you have more
Sure.
questions,
Do you want me to just put your UNC email
yes, that's what
in
I
the Discord
shared.
channel?
Yeah,
Okay.
I shared it
Yeah.
on. Yeah. Please do that. Yeah, I went to school
Okay.
to. Yeah. It's my school email address, and I mostly use it for all professional correspondence. So yeah, please feel free to shoot me a mail, and if there is something else I can do. And yeah, it was great. I had a great time, and let me know if I can talk to you again in sometime in the future. And
Sure. All right. Thank you so much, Sridutt. And
yes.
everybody, please give Sridutt a round of applause or a react or something. But anyways, thank you so much for taking this time out of your day. It was really informational, really great. And also the last question was actually mine from Discord.
Oh, awesome.
Energy efficiency one. Yeah.
So very
Uh,
good.
yeah.
Nice.
Yeah. All right. Thank you so much. And
Yeah.
okay.
Take
Bye-bye.
care. Bye bye.
Yep.
Have a good weekend ahead. Bye bye.